Hello, everybody. May I ask to turn on your camera, please? Thanks. Thanks. I have to explain. Today, unfortunately, I'm very sick. I didn't know whether I should cancel it or not. I preferred not. Try to see whether I could recover a little bit. Let's see how it is goes. Whether I can maintain my sanity a little bit to progress a little bit today. Maybe we finish it a little bit early. Let's see how it is going. But at the end, I decided not to cancel, at least make a little bit of progress as much as we could. Yes, Ross.
Whenever you're feeling better, or just like at any time, would you mind just like maybe briefly going over that the quiz?
Yeah, that's also that was part of the plan. I prefer going over quiz when I feel better. I can
Absolutely.
explain it better, probably, hopefully, or on Thursday. Yeah, today I feel very bad, and like my mind doesn't work, and I cannot explain the way I would like to explain it for you. So you can understand it better.
Right. Well, I hope you feel better.
Thanks. Is there any other question? Okay. For the midterm, also, I will send out over Piazza. Should be on 1st of April. So by then we should finish multi-cycle microarchitecture as well. So you have we cover enough material for the midterm, and also part of the aim for the midterm is to have for you to have some idea how final should look like. But anyway, by then hopefully one or two more homework you will see, and you get a better idea how this looks like. So if you remember, so far what we covered about macroarchitecture, single cycle macroarchitecture. By the way, by macroarchitecture, again, to repeat that, it is important to remember we have two things: the data path, how we put together, we wire things in order to move the data from the right place from it is located, also along the way producing the data and moving to the place that it needs to be stored. So this is what we call the data path. In addition to the data path, it is also important to generate the right control signal. And macroarchitecture is nothing, again, more than these two elements: constructing the data path and generating the right control signal for making all of this to happen. And we covered three types of instructions so far, if you remember. So we covered R type and I type. So let me go over this quickly. We started by R type. Where is this? Yeah, here. We started by R type instructions. Very simple data path that doesn't even require any memory element, if you remember. So it was mainly arithmetic, so we needed ALU here, and it was mainly data coming from the registers and writing to the register. So it was very simple. For all of these instruction data passes, we definitely need PC. Somehow PC is part of this, and the wiring to increment the PC is there for all type of instructions. And this part of the memory where instruction located, and again, we have separated memory into two parts, instruction memory and data memory. We definitely need to retrieve the instruction, and then the rest is just reading and writing to register files. So simple as that. We discussed extensively about this, and I instruction, I type was very similar, but we had immediate where we discussed how to sign extended and do the rest. So the extension from R type to I type was like simple, adding this part regarding the sign extension and few other small changes here in order to make the in order to send out the right bits to these registers, right? So the difference was that the encoding of the bits from R type to I type was slightly different, and we discussed about it. So we needed to add these muxes here in order to distinguish between R type and I type. And then we also had this data movement instruction, load word and a stored word, where we added the new element data memory because we needed to read from the memory and write to the memory. Okay, so here load word, we need to send the right address to the memory, right, and read from the this part from read data and send it back to the register file. This is what happens. So we need to have a little bit of wiring, as you can see, in order to make the data path enabled from memory all the way back to register file. And also for a store word is also similar. We need to send the address similarly to load word, but this time we need to write something here because we need to store a specific word where it is generated somehow from the registers and write it to the memory. And as you notice, we have this control signal, right? So for a store word, since we want to write to the memory, this memwrite should be 1, memread should be 0, because we do not read from the memory. So this sending the right control signal, again, is very important. That's part of the microarchitecture, and the difference here was like this is load word. We do not write to the memory, so this should be 0, but we read from the memory, so memory should be 1. So this is the difference between these two elements, and we discussed about these two type of instruction as well. And this is the data path for non-control flow instruction, meaning that all instruction R type, I type, and data movement except jump type, J type instructions. Now today the plan is to discuss about this control flow instruction, the J type instruction, where it is also this type of instructions very important because without this type of instructions we cannot write interesting programs. As you noticed, for most programs that also you had encountered before, and also you had in your homework, you needed this J-type instruction. So it is important to understand how it looks like at the microarchitecture. So if you remember the encoding, so we had opcode and also immediate address for J-type. So this was encoded in MIPS like J and target. The target address was specified as immediate, and the semantic was very simple. We simply needed to calculate the target address by combining the incremented PC plus immediate by shifting by 2, if you remember. So we needed to shift immediate by 2, or on the other hand, we needed to multiply immediate by 4, and then adding it to PC, incremented PC. And that's what is the target, okay? And simply meaning that we put the target address into the PC, okay? And already by looking at this semantic, you realize that a few things which are important when it comes to the data path. First of all, do we have any access to register file here? Are we reading or writing to any registers? By looking at this semantic, nothing, right? So we do not add, we do not read or write from register. So in previous instruction, we typically either read or write from register, but in jump instruction, we do not. Also, again, other thing that you can see from even just looking at the semantic is that there is no access to the memory. So in this case, there is no reading or writing to the memory. The only thing that happens is basically if you look at this, the whole data path that we have so far. So this part, the right part, I think you see the mouse, right? So this right part is where basically you don't, in this type of instruction, you don't need it. The only part that you need to rewire, you need to add some wiring data path is the part where it concerns the PC, because you want to change the PC. And also definitely at each instruction, you need to read instruction. So you need to have access to the instruction memory as well. So as a result, the control signal that you send, we do not want to write to the memory, 0. We do not want to read from memory, 0. We do not want to write to the register, 0. ALU operation and this mux here all do not care, right? X in this case means that meaning that we do not care, like some part of the data path, if they want, they can use it, but I mean, it doesn't matter. This means that it doesn't matter, but 0 means that like you should not touch this. That's the difference between X and 0. So what is clear is that we need to add some data path here. So and this is how the data path should look like. Already you should know that we need to by the semantic, we need to use these 4 bits from the PC, bits number 28 to 31, the last 4 bits of the PC, plus immediate shifted by 2. So this is what it happens. So you get the last here, the last 4 bits, and you get the immediate from this part, from the instruction, okay? And then you concatenate it here. right? This is what it happens. So you concatenate the last 4 bit of the PC and the immediate shifted by 2, because PC, again, if you remember, it's 32 bits. Immediate is 26 bit. When you shift it, 28 bits, and then you have 4 bits of PC here, these 4 bits that you get from the PC. So you have 32 bits after concatenation. And then you put it into the PC. And definitely here you need a mux, and we already discussed that, right? So mux is an element in the data path, like is a very useful element. Whenever you need to select from like multiple inputs, you add a mux, and then you put the right control signal in order to select the right data path. So this new part is essentially what it enables the jump data path. And this control signal is J, controlling whether it's jump or if it's not a jump, doing the incremented PC as usual. Do you have any question? Is that clear for you? Sorry, again, I cannot explain very well, but if some part is not clear, let me know. Give me a second, I come back. I think it paused. Sorry. Okay, so this is jump or unconditional jump, and you know that we have some variation of jump. For example, jump and link, or jump and link register to register. Jump and link is, for example, jump and link is the case where what it happens is that we need to jump to a location, but we need to save the content of the PC to a register. So, for example, when we want to call a function, we want to jump to a location where the function is located in order to execute the instruction inside the function, but we want to save the current location or the incremented PC to a register in order to come back to this location again after we are done with the function. So we need some data path in order to make this happen. So there is a need for data path from register to PC, and also from PC to register to make this variation of the jump happen. So so essentially there is a need for new wiring between register file and PC, and for each of these we need to again not only the wiring but also the right control signal, because for the unconditional jump there was no need to accessing to the register file, but for these variations we do need to access the register file, so we need to send the right control signal to register file as well, specifically to RedWrite, specifically when we want to write this PC into a register. We need to send RedWrite to 1 in order to make this write happen. And here are the semantic of jump and link. Again, so we put PC, incremented PC into a particular register. It's called return address, and the target is specified very similarly, the same way, and we put the PC target into the PC. So once we want to return, so we use return address register in order to return back to it, and the others in a similar way. I'm not going to discuss in detail. You know the semantic and you got the idea how this wiring should look like. So either from register file to PC or from PC to register file. So it's simple link. The only thing that you need to consider here, and it's important for you to think about it when you're building such data paths. Beside this wiring, one thing that becomes tricky and important is that this control signal becomes complex, as you see. So here, for example, previously, before having this variation of jump, only having even before like jump, right? So before jump, there was no max here, okay? And there was no control signal as is J. By adding this jump, so we needed to add a new element, max, and having a new control signal. By adding these variations, adding this data path, you already know that like with 1 bit, it's not possible to select between 3. So we definitely need more than 1 bit. And adding one more, more and more, basically we require more complex control signal, and the semantic of generating this control signal also become complicated. Not only the more number of bits that we require to encode the control signal, but also the way how you generate the control signal. That's the only tricky part that you need to incorporate. So again, going back to the core concept behind microarchitecture, data paths, control signal, as we add more instruction, data paths, as you saw, becomes more complicated. We add more data paths. Also, the control signal become more complicated. We need to take care of generating the right control signal for the microarchitecture, for particular instruction that we are having. Okay. We have one more instruction, if you remember, which was also very important, conditional branch instruction, B equal, where we had two register, like in this case S0 and S1, and we had this offset. If S1 was equal to S0 was equal, or source register was equal to target register, then we had a jump. A jump happened. So similarly, we sign extend the immediate shifted by 2, and then we add it to incremented PC. That's what it determines the target address, and we jump to PC if these 2 register was equal. Otherwise, similar way, incremented PC. And we had some variation of be equal. BNE, BLEZ, BGTZ. We discussed about it, but these are similarly, these are, in terms of semantic, very similar, and in terms of data path, similar as a result. So what we need here, so we definitely need a new data element to add. So we need an adder here. That's what we added. So we had already a sign extension element here previously, right? If you remember, for immediate type of instruction. So we can reuse this, but we definitely need a shift left element. So we need to multiply by 4 or doing 2 shift left. So we have this, and we need a data path that gets PC, incremented PC, and we need an adder in order to add this together. If these 2 registers are equal, we need to send the result of this add to the PC, and you already see that, like previously we had 3 inputs to this mux, now became 4 by adding this conditional branch data path. I mean, this data path is not complete, and in the next slide you will see somehow the data path, when we put all of these all together, to put this into the context, you see here this shifter here, this sign extended, these add. So whether these 2 elements are equal or not, this is how it happens. You check whether a branch in the first place needs to take place or not by checking a condition, and you know that checking a condition happens in ALU, simply comparing the content, the values of 2 registers, right? So this signal can be condition is generated in ALU, and there is an element control. We haven't talked about it. We will at some point, but these are this is the
sorry, I can't do that right now.
This is the part of the microarchitecture that generate the control signal, right? So you see that all of these control signal has been generated in this element. Okay, do you have any question? Is part of this require any, I'm sure it requires a lot of explanation, and we will clear it as we go, but hopefully you got the idea, at least you got the idea what are the new data paths and control signal comparing with the R-type, I-type, and data movement when we add the jump type and branch condition type of instruction. So now we have a complete picture of single cycle microarchitecture as a result. About the control signal, so this is the last part that I want to cover today, and then you can stop. About the control signal. This is how the control signal are generated by combinational logics, right? And in this table, on the left-hand side, you see this the name of control signal, right? So, for example, RedWrite. If you remember this last row, RedWrite was the control signal for the register file. This one, this guy, which determined whether if it was 1, meaning that we could write to the register file, we could change the value of the register. If it was 0, meaning that we could not write to the register file. MemWrite, similar way, was the control signal that was determined whether we should write to the memory or not. MemRead, this one, was basically determining whether we read from memory or not. Similar way, right? So here is basically specifying how we could generate this control signal using combinational logic. And this combinational logic, one thing that you need to consider is that and we will explain it a little bit in more detail later on. But basically, almost all, except one which we require we require some data that is generated during the data pass. The only thing that we need to know is is part of the encoding from the instruction, right? So basically the opcode of the instruction. For example, for RedWrite, RedWrite is one if opcode is a store word, is not a store word, or not jump and register, or not branch condition, right? So in this case, RedWrite is enabled. Otherwise, is disabled, right? So and like in this case, we know that, like, for example, for a store word, like, we know we don't need to write to the register file in jump, in branch, in none of these we require to write to the register file, so we need to set it to 0. Similar way, for example, for mem to register. Mem to register was where is this mem to register? This guy. This is mem to register. This control signal is when it's set to 1, meaning that we can write from the content of the memory would be written to register file. And you know that the only instruction that we require this contour signal to set to 1 is for load word, because we need to load the content of the memory, the word that we read from the memory, write it to a register, into a register file. And when this condition is true, meaning that this contour signal is set to 1. But you got the idea. So basically this contour signal is generated using the combination logic by checking this equation, by evaluating this equation. This is essentially how this control is implemented. So this is a combination logic that by evaluating this equation, generate the right contour signal for this microarchitecture, single cycle microarchitecture. And one thing to clarify, so as you see, almost all of this only require the opcode, except this one, which require like B condition is satisfied, right? So and B condition is something that is generated during the data pass. Is not part of the opcode. So B condition is generated in ALU in data path, so there would be a need of some calculation, like comparing two register value and generating and the right, for example, whether this branch condition is satisfied or not. So it's not only dependent on the opcode, but also dependent on the on some calculation along the path. So you need to contrast this as well. Let's stop here. I think I cannot talk or I cannot think more than this. Sorry about that again. But just wanted to cover this part of the material so we could make some progress. Thank you, guys. Thank you so much.
Thank you, Professor. I hope you start to feel better soon.
Thank you. Thank you.